Hello, welcome to my brief presentation on some of the proofs that I wanted to demonstrate from Stepbil's Introduction to Brownian Motion video. I thought that was a very informative video for those who didn't quite understand the concept of Brownian motion, and Stepbil was able to actually demonstrate these concepts in a very well manner. So I'm very thankful for that video myself, especially as I was taking a course on stochastic calculus. So I wanted to prove some of the statements that Stepbil made. Some of the properties are just part of the definition of Brownian motion. So here I'm going to use W of t as the as representing standard Brownian motion. Some might choose to use bt or b of t. Personally, I just stick with W because in some textbooks they use bt to represent the Brownian bridge, and also the WT is also just characterized by what it is, which is the Wiener process that's also named. Some people also use W sub t. Since it is continuous, I prefer using the subscripts for discrete time processes, just like when you study functions, you use f of x for functions, and then you use something like an or of such, or xn for sequences, for instance, which are discrete based and these are continuous. So for the purpose of talking about Brownian motion, I'm going to be using this as the notation for it, for standard Brownian motion. So I wanted to first prove the covariance statements. So when you take the covariance of two Brownian motions at different times, so say Ws and Wt, it's just going to be the minimum of the two times. So the way I denote that is with this symbol here, which just means the minimum of S and T. And let's figure out why exactly that is. So let's suppose let's actually make our time indices a bit clearer. We can do this kind of like a without loss of generality statement. So without loss of generality, let's suppose that t is between 0 and s. Okay, it could be s between 0 and t, but for this purpose I'm just going to use t to be the index between 0 and s. So in a time diagram sense, this is 0, that's t somewhere here, and then this is s somewhere here, right? So this is our time frame of reference that we've created. So how do we compute covariance of two processes or two random variables? Well, we know that the covariance of two random variables is just taking the expectation of the product, right, minus the individual expectations multiplied, right? This is the formula for covariance that I know of. There's other ways to do it, but I'm going to be using this formula itself. So if we apply this formula to what we're trying to show, right, we take the covariance of Ws, Wt, it's just going to be the expectation of Ws times Wt, right, minus the individual expectations, right? Okay, so this is what we have, and question to you is, what is the distribution of Brownian motion? Well, you know from Stepbil's video that Brownian motion is normally distributed, right? We know that Brownian motion is distributed normally with mean 0 and variance t. Or in other words, it's normally distributed with mean 0, variance t, right? This is the way I usually like to denote it. It just makes it a bit easier when you actually work with expectations. So I'm going to be using root t times z as the way I write the distribution, and I write it with an equal sign above. So that means that the mean of Brownian motion is 0, right? And it's the same thing with Ws, right? So that goes away. So all you have to look at is this piece here, the expectation of Ws times Wt. So let's find out exactly what that is. So take the expectation of Ws times Wt. Well, we know that S is bigger than T here, right? So what I might want to do to help with this expectation, since we can't do much at this point, is to take a look and see if we can actually create a Brownian increment from this. What I mean by that is, so we can, let's pull out the Wt, and let's do Ws minus Wt. Right, so let's make the increment Ws minus Wt from this guy here. Right, so I'm going to subtract a Wt term, so that means I'm going to have to add it to make this expression the same thing, right? So minus W squared plus W squared, that cancels out, so you just get Wt times Ws, or Ws Wt. It's the same thing, right? So by additivity of taking expectations, right, it's just going to be each one separately, so Wt times Ws minus Wt, right? Plus the expectation of W squared, right? And since we know that the first moment of it is equal to 0, that makes the fact that the variance, right, of Wt, so by definition, this is just an aside, right, and that goes away because that whole thing is equal to 0, right? So in other words, the second moment is equal to its variance, which is just equal to t, right? So this part here is equal to t. So the next part to consider is that you have this increment here and Wt, right? Above, if you look at our time diagram frame of reference, if you think about Brownian motion itself, from within these times, you know that W of 0 is equal to 0 by definition of Brownian motion. Every Brownian path starts at the origin, almost surely, with probability 1, right? Brownian motion at this time here is Wt. Brownian motion at time s is W of s, right? So when you take the increment of Brownian motion, let's draw this. So let's say we have, time, and then you have W, right? And this is just a little, I know this is a little like sudden, but I want to explain what's sort of going on. I'm not going to write that there. So let's say this is T, and then this is like S, right? And we know that every path here starts and does crazy things, right? So if we think about it, this part here, you're looking at Wt minus W0, right? Which is just Wt, right? Since W0 is equal to 0 by definition, right? From here, you're looking at the difference W of s minus W of t, right? And because they're non-overlapping time increments, the Brownian increments themselves are independent, right? It's the fact that since the time parts are separate from one another, right? W from 0 to t is separate from t to s, right? If you take a look at this, there's no overlap in these two increments, right? So that means these two paths here are independent. And this is because Brownian motion itself has stationary and independent increments, right? Which is something that Stepbil looked at in point number 3. But because this expectation is 0 and so is this, then you're just left with t, right? Now, as I stated above, t was the one that was between 0 and s, right? T was the minimum. So if we synthesize what this is, the covariance of Ws Wt, so it was t, right, for t less than or equal to s, right? And so without loss of generality, it would follow the other way around. And so another way to synthesize this is just to write this as the minimum of s and t. So that completes the proof of the covariance part. So I'm hoping that clears things up. So let's move on to the next part, which is talking about how Brownian motion is a Markov process or a Markovian process. So let's write the actual definition of what it means for a process to be Markov or Markovian. So definition. So a process or a stochastic process, let's call it, say, xt, where t has its own time indices. It could be t bigger than or equal to 0. I'm just speaking just generally in terms of processes, is Markov. Okay, is Markov if for any Borel function, call it, say, h, and then for any time in the time interval that we're speaking of, for all the set of time indices, there is another function, there is a Borel function g, such that the following expectation holds true, so that we take the expected value of h of the process conditional on the natural filtration on the x process up to time s being equal to that Borel function of the process at time s. And this is for all s between 0 and t. Okay, so this here is the natural filtration of the x process up to time s, up to time s. So let's prove, using this definition, that Brownian motion is Markov. So Brownian motion w of t is Markov or Markovian. So let's so in order to prove this statement, we need to fix this function here. We need to fix a function h, and then show that there is such a g that exists, such that that expectation statement holds true, right? So we're going to let h be a real-valued function, real-valued Borel function, be a fixed Borel function. And we're going to let this guy here be the natural filtration for Wt. And basically what I'm just saying is that this guy here is going to be defined as the natural filtration of Brownian motion. Okay, so we've constructed our filtration, we've fixed a Borel function. Now we need to show, so we are required to show that there is another real-valued function g that is real-valued, such that the expected value of h of Wt conditional on the natural filtration for Brownian motion is equal to another Borel function valued of w of s, and this is for s between 0 and t. So all I've done is I've just basically written the definition above here. So we need to look and start from this point. Right, so this point here, I'm a little lazy to write the whole thing out. So I have something in terms of t's, I wanted it in terms of s's to remove this conditional expectation, right? The whole goal with conditional expectations is to bring them to be non-conditional regular expectations. You don't want the condition to be there so you can evaluate what the expected value of the process is. So I can write this as, Wt minus Ws plus Ws, right? Conditional on f of s. So again, with our time frame of reference, with this part here, This is 0, this is s, and this is t, right? And from here, you're looking at t minus s, take that difference. So this difference here is t minus s. This difference to 0 is just s. Do we agree? Yes, we do. So now I know, and from before, just kind of with the example I did with the covariance part, we know then that w of s and w of t minus ws are going to be independent, right? Because if you think about it, just like with the other explanation I did before, this is 0, this is s, and this is t. That's Brownian motion somewhere, right? Because the time indices themselves are going to be, they're non-overlapping increments. That means the Brownian increments themselves, these two Brownian increments are going to be independent, right? This part here is wt minus ws. This part here is just ws, right? Since w of 0 is equal to 0, right? Every path starts at the origin. So I can use that fact and define, say, x to be this increment here. So let's define x to be this, wt minus ws, right? And we know that this part here, it isn't fs measurable, but it is independent of this filtration, right? So we know that x is independent of the natural filtration up to time s, right? And then we know that ws is clearly fs measurable, right? So if you write that expression down, then you end up with taking the expected value of h of capital X plus w of s, right? Conditional fs, and it is equal to g of w of s. So it is a function of ws, where we now define the general function for this thing, where we define g of x, so g of little x, to be the expected value of h of capital X plus x, right? Because if you think about it here, at this point, you don't actually need the condition, because we know that x is going to be independent of the filtration, and then w of s itself is already fs measurable. So if I want to write another step, it should have been capital X plus w of s, right? And then that will be a function of ws. There you go. Sorry about that. We define g of x to be this expectation, and since we know the distribution of the Brownian increment, we know that w of t minus w of s, if you watch Stepbil's video, it's going to be a normal distribution with mean 0, and then variance t minus s, right? So it's going to be root t minus s times z, where z is normally distributed with mean 0, variance 1. And so you can actually evaluate what this function is, right? If you think about expectations, they're really just integrals, right? So I'm going to quickly write the next step. So it's just going to be root t minus s times your standard normal plus some arbitrary x, right? Okay. So by definition, when you start constructing the expectation is basically just the integral, right? So you're going to go from negative infinity to positive infinity, and then you're going to put in whatever that's going to be taken of expectation, right? Times z plus x, right? So it's going to be h of that whole thing times the standard normal PDF. 1 over root 2 pi e to the negative z squared over 2 dz, right? So because we found a Borel function, which this is because this is just the integral, right? You have the standard normal PDF, and you have another Borel function. We know that g of x is Borel, and so by construction here, we have shown indeed the existence of this. And so by definition, it means that Brownian motion is Markovian. So the result follows. Next thing to prove is to show that Brownian motion is a martingale. Okay, so let's show that. So next one, this I think is number 5. Brownian motion WT is a martingale. So there's generally 3 things to show that a process is martingale. The first one is to say, is the process adapted to the filtration Ft, where T is bigger than or equal to 0. So additivity, or Ft measurability for all T. Well, we do know that it is adapted because Brownian motion is adapted to the natural filtration, of Brownian motion. Right? And since it's adapted to its own natural filtration, it's adapted to this guy. So that proves the first part. Second thing to show is that it's integrable. Integrability. So basically we need to show that taking the expectation of the absolute value of Brownian motion is finite. So let's demonstrate exactly why that is. Once again, I'm going to be using convenient notation that we know that this is normally distributed with mean 0, variance t, otherwise written like this. So this is just what I'm going to be writing for convenience sake. So if we take the expected value of the absolute value of Brownian motion, we know right away it's just taking the absolute value of root t times z. Clearly this is positive, so the absolute value brackets only have to go around z, right? And we can actually pull out the root t, since it's just a constant, right? You can pull constants out of expectations like you pulled out of integrals. So it's going to be root t times the expected value of absolute value of z, and this is not 0, so we have to evaluate this by the definition. So I hope you remember how to evaluate expectations. So we're going to go from the whole sample space, which is defined on which is all real numbers, and then it'll be absolute value of z over root 2 pi, right? E to the negative z squared over 2 dz, right? So because this guy here is symmetric, I'm just going to use a quick little trick and just do, and let's just only consider, if we're going to have to consider the whole set of real numbers, let's just multiply it by 2 and only go from 0 to infinity. I think it'll make it a lot easier to evaluate this way. So 2 times root t, going from 0 to infinity, and since we're going from 0 to infinity, since z is going between 0 and infinity, absolute of z is just equal to z, right? I'm sorry for kind of my ugly handwriting. It just gets kind of hard writing the tablet for a long period of time. I'm going to try and get used to that. So I hope by now you remember how to evaluate an integral using integration by parts, but if you forgot, I'm going to write that on the side. So let u equal to z squared over 2, so that means du is equal to z dz, right? And then we know that obviously u of 0 is just going to be 0, right? Plug it into here, 0 squared over 2 is 0, and then u of infinity will kind of get us infinity, right? So the bounds don't change, in fact. So it'll be 2 times root t, I'm going to pull this guy out, over root 2 pi, and then you're just going to be integrating from 0 to infinity, and since that guy is going to be the z dz just gets replaced with du, we're going to have e to the negative u du, right? This integral just ends up becoming negative e to the negative u, evaluated at 0 and infinity, which is just equal to 1, right? Because you're going to get e to the negative infinity, which is 0, minus negative, right? Double negative becomes a positive, so you're going to be plus e to the 0, which is just equal to 1, right? So that means here 2 divided by root 2 is just going to be root 2 on top. So you put everything under square root, you're going to get 2t over pi. And clearly that is finite for any t that is finite, right? So we've demonstrated that the expected value of absolute value of wt is finite, which means it is integrable. Okay. Now we need to show the last step, which is called the Martingale property, which is probably the most important property when it comes to looking at martingales, which is the property that Stepbil actually elaborated on last time in his video. So the Martingale property. The Martingale property. So I'm going to be letting 0 less than s less than t. So again, time frame reference here, that's 0, this is s, and this is t, right? So what we need to show is that taking the expected value of the future value of the process, so looking at Brownian motion here, conditional on the filtration up to the value up to time s. So all the information that we have up to time s is just equal to, so that this expectation here is just equal to, well, it's just equal to the Brownian motion evaluated at what we know today. So let's prove this. So if you take the expected value of this guy, conditional on f of s, kind of like what I did with another trick before, we can subtract the ws and add it, right? Because we want this in terms of time s indexed values, right? So wt minus w of s plus w of s, conditional on all the information that we have up to time s. Now, if I draw another graph on Brownian motion, I'm going to try and get this a little neater this time. So every path starts at the origin, that's for sure. Let's make s here, and let's make time t like here. And let's say I'm going to go up and down and whatever. Things go crazy all over the place. So if I look at my points of Brownian motion of wt minus ws, that is precisely looking at this region here. Likewise, w of s is also the same thing as just w of s minus w0. So you're going to go from here to the origin. And then this part here is going to be w of t minus w of s, right? So once again, the time going from 0 to s and t minus s, those are non-overlapping increments. So that means the Brownian motion increments are also going to be independent, right? So that means we know that wt minus w of s is independent of f of s, right? So that's the first fact we know. And the second fact that we know is that, once again, Brownian motion is fs measurable for w of s, right? It's measurable by the first property. Is fs measurable? Right, we have all the information up to time s, so it's measurable in that sense, right? So when you take the additive property of computing expectations, then you end up getting left with wt minus w of s, conditional on f of s, plus expectation of ws, conditional on f of s, right? So since we know that this guy here is independent of f of s, this just becomes a regular expectation, no more conditioning. In which case we know that this is equal to 0, right? Because this is just another, this is just normally distributed again with mean 0, variance t minus s. And then this part here, right? The expected value of w of s conditional on this, well, you can just pull that out of the expectation, right? Because this is fs measurable. So it just becomes w of s, which is just w of s plus 0, so it's just w of s. And so since we've shown that it works for s between 0 and t, that means the Martingale property holds true. And I know I did write it a bit differently than the way Stepbil demonstrated it, but I'm hoping that that might explain the concept a bit more. So thank you very much for watching and stumbling upon the video. If you did find it informative, I encourage you to share this video with other people, and I'm hoping to perhaps continue explanations on Brownian Motion. I want to thank my instructors who taught the course and taught the program. I am a recent graduate from Wilfrid Laurier University's Financial Mathematics program, and I look forward to making more videos in the future if you did find them to be very useful. So have a good day. Thank you very much.